All right. Can everyone hear me? Perfect. Welcome to United Astronomy Clubs of New Jersey. Thank you everyone who is joining us here in Jenny Jump State Park in Hope, New Jersey, and everyone who is joining us online, because that's right, we do actually live stream these talks on both YouTube and Twitch. So if it's ever rainy in your home on a Saturday night at 8 p.m., feel free to join us there online. If you're online, hit those like and subscribe, because it does help us know that we're actually, you can hear us. So I think we have a couple people still parking, so to give them a couple minutes to wander on down and find a seat, I want to invite everyone to check us out on our website, uacnj.org. It's where you're going to find a list of all our upcoming talks, all the talks we've had in the past, with links to watch those on our YouTube archive. In addition, you'll see a page where we list all our member clubs, because that is right, we are actually a club made up of other clubs, and one of the easiest ways to get into astronomy is to find your local club. So I know we have a bunch of scouts, so if you get on Google, search our website, find the closest one to you. They might have some good tips and tricks for astronomy out by you guys, because I don't know quite where you guys are from, because I don't have my distance glasses, so I can't actually read your shirts. Nice. Mawa. That's not too bad of a drive, though. In addition, you can check us out on our social media pages. It's a great way to see what we're doing that week, as well as any special events that we might be up to. That is our Facebook, Instagram. We have a Discord server, and those are also all great places. If you have any questions, ask them there. I do check that regularly to try and get answers out to you as quickly as possible. So it looks like we're almost down here. So we're going to get into the safety briefing for those of you who are here. If you need to use the restroom, that is the porta potty. It is big. It is blue. When it gets darker, you will see that it is illuminated by red for ease of finding it. We also have a little museum area and gift shop, and I will be manning that after the talk, because I still am not allowed to break the laws of physics and be in two places at once. Once I do, I can take over the world, but until then, you'll find me there after the talk. We have a little meteorite display. If your scouts like patches, we have some available through the gift shop, like I said. In addition, each of those sheds that you saw when you were parking actually houses its own telescope. The ones with the roofs rolled off and who have volunteers set up in front of it, feel free to ask them what they're looking at if the skies cooperate with us. And if they don't, they'll at least show you what a actual telescope in our setting looks like. Feel free to ask them questions. They love to answer, and sometimes make up answers if they don't know, because I know not everyone memorizes the distance from Earth to Saturn. Mm-hmm. Someone was like, I don't know. How am I supposed to memorize those facts? I'm like, we have the portable internet boxes. All right. So, for all the adults in the crowd, when we go to leave, we are using our headlights. We do not want to get run over. I am sure you also feel the same way. Having our headlights on does help us accomplish a zero injury night. That being said, I notice a couple of us have flashlights and lanterns. We do try and keep those lights pointed towards the ground because we don't need to accidentally blind people when we're having flashlight raves and whatnot. So like I said, do try and keep those pointed towards the ground just so we don't accidentally blind people. With that, you're not here to hear me blabber on. You're actually here for a lovely talk by Nathaniel Frissell. I said your name right.
You did.
Okay. Nathaniel has a PhD, and he doesn't say what it is for, but
I can introduce myself. It's okay.
You want to introduce
Sure.
yourself?
Yeah, because I actually want to say something about the Scouts.
Okay, perfect. Well, here's Nathaniel.
Thank you so much, Kim. Thank you. Hi, everyone. How are you? Good. Good. Yeah, so my name is Nathaniel Frissell, and I do have a PhD in electrical engineering from Virginia Tech.
Hey, Nathaniel.
Yes?
In order for online people, you have to be behind the white
people.
line.
They're right there.
Yes.
Okay. All right, I have to stay put. So my name is Nathaniel Frissell. I do have a PhD from Virginia Tech. I did my undergrad at Montclair State University, so I'm sure many of you know that. And I'm originally from Bloomfield, New Jersey, so I'm a New Jersey person at heart. I eventually did, after Virginia Tech, I did my postdoc and a research professor at New Jersey Institute of Technology, and that's how I started doing some work here at Jenny Jump, because they have instrumentation. NJIT has instrumentation here. And then I got a tenure track position at the University of Scranton, where I'm an associate professor of physics and engineering at the University of Scranton, and I continue doing the work that I'm going to talk to you about tonight. And I continue to collaborate with NJIT and host Put Instruments over here, which again I will talk to you about tonight. But what I wanted to say about the Scouts is Scouting is actually what launched my entire career. Because when I was a Scout, probably in 7th or 8th grade, which is a little older than you are in the Cub Scouts, I learned about ham radio. And I learned about it at Camp Glen Gray. Have you heard about Camp Glen Gray? Some of you have, yeah. So one cold, wet, rainy weekend in October, probably about 30 years ago, I went on a camping trip to Camp Glen Gray, and there was a little cabin in the woods that there was a guy, Greg Nitkowski, N2BSA, that had a ham radio station set up in there. And we were supposed to be out doing Paul Bunyan woodsman work, but it was really cold and wet and rainy, so I went in that little cabin. I learned about ham radio, and Greg was talking to people all over the world, not with a cell phone, not over the internet, but by bouncing signals off the upper atmosphere like you'll hear about in a few minutes. And that launched a curiosity that just drove me through my entire career. I eventually got my own ham radio license. I went on to teach ham radio at Forestburg Scout Reservation and at Maine National Scout Jamborees, and I became an Eagle Scout. And certainly without scouting, I would not be here today. So I just want to encourage all of you Scouts to continue doing what you're doing. My son he's going to be a Tiger this year, so I'm very excited about that. Okay, so the title of my talk is HamSCI, Space Weather We Can Do Together. And this is where, we have amateur astronomy out here where people are able to look at the stars through telescopes, and sometimes amateur astronomers have connections with professional astronomers. They're able to work together. I do the same thing with space physics. So beyond just looking at the stars, space physics looks at, say, the aurora. It looks at the effects of solar flares, geomagnetic storms, things like that, the solar wind, how it impacts our magnetosphere, and something called the ionosphere. And the way we do that is with something called amateur or ham radio. Now, how many people here are amateur or ham radio operators? Can you raise your hand? Okay, we have a couple. Are you in the Scout group? No, you're not in the Scout group. I was going to say if he was in the Scout group and you want to learn more, you could go talk to him. But yeah, if you become interested in ham radio, just the same way, if you want to become interested in astronomy, you look up astronomy clubs. You can look up ham radio clubs in your area. And after this, if you want me to help you to find some in your local area, I'd be happy to do that. So what is ham radio? Ham radio is a hobby for radio enthusiasts, and it's for communicators, builders, and experimenters. Ham radio operators aren't the type of people that play music on the radio. In fact, we're not even allowed to. We don't broadcast the news, but we're very interested in two-way communications and often talking to people as far away as possible. We're also interested in building and designing and experimenting with radio devices. And ham radio operators, they come from a wide-reaching demographic, all ages and walks of life. So there's over 760,000 hams in the United States and about 3 million worldwide. And some of the youngest have become ham radio operators as young as 5 years old. And some people are ham radio operators well past 100. So it's really neat. Now, what makes a ham radio operator? Ham radio operators are licensed by the federal government, and you do that by taking a multiple choice exam. And on that exam, you have to know basic radio frequency, electrical engineering knowledge. And this is really great for citizen science because it provides a path to learning, and you learn all the fundamentals. So if you want to become a ham radio operator, there's a website and there's some books that you can read and people that can help you learn the material, but it's definitely something that younger people can do. And people who are, more experienced, they might be interested in it as well. The way you can know a ham radio operator is by their call sign. So when you get a ham radio license, you get a call sign that identifies you on the air. So my call sign, personal one, is W2NAF. W means I'm from the United States. 2 means I got my license originally in New York or New Jersey. And then NAF could be some systematically assigned letters. In my case, I actually paid a small fee and got my initials. The university I work for, our call sign is W3USR for University of Scranton Radio. And NJIT, that also I collaborate with, they are K2MFF. So ham radio is generally a hobby, but it's greatly affected by space weather, and there's a professional science component to that. So while I was in graduate school studying for my PhD, I came up with this idea to create a group or organization that we call HamSCI, the Ham Radio Science Citizen Investigation. And our job at HamSCI is to come up with ways to connect the amateur radio community with the professional science research community in this field. And we've been very fortunate. I've been very fortunate. I've been able to generate quite a bit of funding through federal grants from the National Science Foundation, from NASA, and from a private foundation called ARDC. And some of those foundations and NSF, they've provided the funding for our research instrumentation here. So how does all of this work? How many people here have heard of something called the ionosphere? Right? A few people. So way up in the sky, if you go about, 300 kilometers up above the sky, would you believe that the gas up there is electrified? It actually is. So the gas at 300 kilometers altitude and higher is electrified, and we call that the ionosphere. The reason it's electrified or ionized is because ultraviolet energy from the sun hits our neutral atmosphere and knocks off electrons from the neutral particles. And so you have something called a plasma, which is a gas that has free-floating electrons and free-floating positive ions. And the reason this is important for radio is that electrified layer is reflective to certain radio frequencies. So normally if you took like your cell phone or most radios, they would, if you were to transmit, it would actually cut straight through to the sky, and that's how you do radio astronomy. But if you're on certain frequencies, the ionosphere will bend those signals back to Earth and will let you talk to places like Australia or Norway or something like that. Now, the ionosphere is structured a bit. So in this figure, you can see that there's a daytime ionosphere and a nighttime ionosphere. The daytime ionosphere is stronger because the sun is constantly there ionizing the ionosphere. At night, the sun goes away. Part of the ionosphere becomes weaker because some of those free-floating electrons find their neutral ions, or find those positive ions, they recombine and become neutrals. It becomes weaker, but the ionosphere doesn't completely go away. But it's important for you to know there's a difference between the daytime ionosphere and the nighttime ionosphere. The other thing that's important to know about the ionosphere is how we name these different regions. You can see that the ionosphere has different regions or layers. So the one closest to Earth that only appears during the day is called the D region. Then right above it is the E region, and then you have the F1 and the F2 region. At night, when the ionosphere becomes more simple or weaker, you pretty much just have the E region and the F region. Some of these regions are better for radio propagation, so the E and the F1 and the F2 region, they can help our radio signals go far. The D region is usually pesky. It often absorbs the radio signals, so we often don't like to use it too much in ham radio, so it kind of gets in the way. But there are different ways you can get around it sometimes. Anyway, the main way that we do radio propagation, if you have radio signals between say 3 and 30 megahertz, the radio waves can bounce off the ionosphere through something called skip propagation. Now I don't know if you can see this very well. I'm going to play this little movie. Are you able to see that at all? Okay, good. So you can see here's a radio transmitter in California. Here's a radio receiver in Pennsylvania. This is what we call a ray trace. We are on 14 megahertz. The signals are going up to the sky, bouncing back down, and when the conditions are right, California is able to talk to Pennsylvania. See, now we're in the middle of the night. All the rays are escaping out into space, so California can't talk to Pennsylvania. But in a few minutes, and I can fast forward this a little bit, it'll be dawn, and the ionosphere is going to get stronger, and the radio waves are going to be able to bounce back towards Earth. And you're going to see that now the red line appeared. California can now talk to Pennsylvania again. So these radio connections, they don't always work. Sometimes they work, sometimes they don't. But by observing these radio signals, you're actually able to remotely sense something about what's going on in the upper atmosphere, in the ionosphere. Here's another ray trace I want to show you. This one shows you the same background ionosphere, but it's showing what happens with two different frequencies. So here's a 15 megahertz frequency. You can see that it takes only a single hop to talk 1,500 kilometers away. If you go down in frequency to 10 megahertz, it takes 2 hops to go that same 1,500 kilometers. So going lower in frequency, the radios bend more, and you get more refraction. When you go higher in frequency, you get less refraction, so you can talk farther. But if you go too high in frequency and the radio signals don't bend enough, what happens to the signals? They just escape into space and you can't talk to anyone. So remember that. Okay, so let me show you a picture of what a ham radio station might look like. These are some pictures from my house. Since I moved from urban New Jersey, I now live in kind of rural Pennsylvania. So here's my house, and my ham radio station's in here. And this is my antenna up here. It's just a wire that goes between a couple of trees. It's not a very fancy, expensive setup. Here's the ham radio station. So that's the actual transceiver right there. I also have a software-defined radio where you can get these really cool displays of the different things you're listening to. And now I'm actually going to play for you what a ham radio contact might sound like on these HF high-frequency bands. This I recorded at my house on 14 megahertz a few years ago. This is a spectrum that you're seeing with many different conversations. That's a conversation, that's a conversation, that's a conversation, that's a conversation. We are going to listen to just this one over here. I'm going to play it twice so you can try to hear what they're saying. Do you guys know the phonetic alphabet? Like instead of saying A, B, C, D, you might say Alpha, Bravo, Charlie, Delta. They're going to use that type of language here. So you might hear things like Norway, and they don't mean Norway, they mean the letter N. So keep that in mind while you're listening. That might help you to understand what they're saying. That.
Thank you. From Lima Yankee number 3, number 1 Alpha. PSS station from New York. Whiskey Echo 2 Charlie Alpha Tango 59 Pendelis John. January, October, November. Good morning.
That's someone tuning up
Okay,
time.
Sussex County, New York. State.
All right. Did you get the person's call sign? What was the call sign? Okay, so he was talking to someone in New York, but the person that we were listening to speak, his call sign was LY31 Alpha, Lima Yankee 31 Alpha. And he was actually in Lithuania. So I was listening in Pennsylvania to this guy who was talking from Lithuania over here, 4,200 miles away. And this did not go over the internet. It did not go through satellites. It just went off the upper atmosphere. Let me play it one more time and listen for that Lima Yankee 31 Alpha. See if you can hear that person's call sign.
Thank you. From Lima Yankee number 3, number 1 Alpha.
Did you hear it that time? Okay, yes. I see people have questions, but I've been asked to hold the questions to the end. So try to write down your question or make a note of it, and then at the end I'll answer everyone's questions. Okay, so as I said, these signals don't work all the time. We pick up our cell phones and we expect it to work all the time, right? Okay? It doesn't work like that with these high-frequency radio signals, and actually that's what makes it interesting. That's what helps us to solve the scientific puzzle. And the scientific puzzle is understanding what we call the geospace system. So what is the geospace system? Well, geo means Earth, so the geospace system has to have the Earth in it, and then space is the space around it. What space do we mean? We primarily mean the Earth, the Earth's magnetic field, what we call the magnetosphere, and the main thing that influences that is the sun, our closest star. So the sun puts out a solar wind that's constantly blowing towards the Earth, and that solar wind has a magnetic field embedded into it, what we call the interplanetary magnetic field, or the IMF, and that puts a pressure on the Earth's magnetosphere, and that's what gives it this funny teardrop shape. So it's compressed on the day side, stretched out on the night side, and there's all sorts of interesting and fantastic physics that happen in this magnetosphere, including the northern lights and the aurora. In addition to the magnetosphere, this magnetosphere will come down and it'll thread the ionosphere, and these magnetic field lines can actually drag the ionosphere around. So things that happen out in space can directly affect the magnetosphere, the ionosphere, and the radio signals that we're listening to. Now, one of the most dramatic types of space weather that we experience in radio comes from something called a solar flare, which you can observe optically. But it also puts out a tremendous amount of X-ray energy that affects the ionosphere. So here's a solar flare. We call an X-class solar flare. This was observed by the NASA Solar Dynamics Observatory spacecraft, and this is an X9.3 class solar flare. And this is actually going to cause a radio blackout of those signals between 3 and 30 megahertz. How does it do that? The X-ray energy causes that D region ionosphere to become extra ionized. The D region absorbs the radio signals. And so with amateur radio, you heard someone talking, but amateur radio operators also use Morse code, and they also use digital signals. Computers talk to each other, and we have automated systems like the Reverse Beacon Network, WhisperNet, and the PSK Reporter websites. We have receivers all over the world, including one in that shed over there, that are listening to these ham radio communications. And we can go look at those communications during a solar flare, and we can see how the solar flare affects the radio communications. So this is a plot that I made for that X-class solar flare. The top map is the ham radio communications in a 15-minute period before that solar flare I just showed you. And during that time, there were over 13,000 communications that were observed. In the immediate 15-minute period after that solar flare, there were only 2,500 communications. So that solar flare just wiped things out. You can see it even more dramatically over here. So this is there's actually two solar flares here. There's one and there's the other. I think this is the one that you saw the movie of. And this is a map over, this top plot is 7 megahertz over Europe. The bottom plot is 7 megahertz over the United States. Let's just look at the European one here for a second. So the European, we're looking from 6 UTC to 18 UTC. So we're looking at 12 hours worth of time here. And this is distance between the transmitter and the receiver. So you see lots of radio going on here, and then boom, it goes away because of that solar flare. Lots of radio, boom, it goes away because of that solar flare, and then it recovers. So the radios can recover from the solar flare in about a half hour to an hour or so. Now, if we look in the United States, you can see that the United States wasn't really affected much by that first solar flare, but the second, a little bit more, but not too much. Does anyone have an idea why? Why was Europe so affected by the solar flare, but the United States was not? Yes, all the way in the back. Exactly. Europe was facing the sun at that time. Good job. So yeah, the solar flare affects most the part of the Earth that's facing the sun. The United States was on the dawn flank, so it wasn't affected so much by the solar flare. Okay, another quiz question. What well-publicized astronomical events took place over North America on October 24th, 2023? I think that should say 14th, 2023, and April 8th, 2024. Yes, what's that? There were solar eclipses, that's right. There was an annular solar eclipse on October 14th, 2023, and a total solar eclipse on April 8th, 2024. And so there are some pictures from that. Who answered the last question right there? You get, oh, this is good. So if you answer questions correctly, you get a prize. I like this. So, so with everything you learned about ham radio and day and night, in the ionosphere, do you think solar flares might affect ham radio signals? Yeah, you're absolutely right. And so because of that, we created something called the HamSCI Festivals of Eclipse Ionospheric Science. So myself and my team, we organized an event with people all over North America, and even into Europe. We had people in Great Britain participate too. Get on the ham radio and try to see how the solar eclipses would affect ham radio. And here is one of my colleagues, Dr. Joe Huba, ran this model of the ionosphere during the total solar eclipse. Now, you've probably seen movies of the eclipse that looks similar to this. Is that right? You haven't seen it? No? You haven't seen like the shadow? You've probably seen the shadow. If you have seen a movie that looks similar to this, it's probably because you've seen a movie of the shadow of the moon moving across North America. This looks similar, but it's actually different because this is a physics model that's not showing the shadow of the moon, but rather it's showing the electron density depletions predicted for the eclipse. So this is actually the ionosphere. And similarly, we can take those models and we can put into these ray trace diagrams. And right now, Florida can talk to Wisconsin, not anymore, on 14 megahertz. The reason it went away in that model wasn't because of nighttime, it was because of the eclipse. So for our festivals of eclipse ionospheric science, we actually had a lot of different experiments going on. I put at least 5 of them up on the slides. I'm only going to talk to you about the results from 2 of those experiments today. One is called the Solar Eclipse QSO Party, and the other is called the Personal Space Weather Station HF Doppler Experiment. And the Solar Eclipse QSO Party, first of all, you should know something about a QSO party. That's like a contest where ham radio stations try to talk to as many other ham radio stations as possible during a certain amount of time. So we made that contest during the eclipse. And before I show you the results of that, I want to show you where at the university I work at, we got a new ham radio station put in so that we could also participate in the QSO party. So yeah, I'm from the University of Scranton. This is a Jesuit liberal arts university. We have about 5,000 students. We're all located about an hour west from here. And we have undergraduate degrees in electrical engineering, computer engineering, mechanical engineering, physics, if you like astronomy, and more. And this is a picture inside of our ham radio station that we just got put in last year. We have an absolutely fantastic ham radio facilities there. We have a nice big tower on the roof. For those high frequency bands, we can talk to satellites, we can do local type of communications. This is where our station is located. And here's a little video the local news station did about the W3USR and the solar eclipse QSO party.
Students in Lackawanna County are learning more about radio waves and their connection to the atmosphere and to space.
It's part of a large research project at the University of Scranton. Newswatch 16's Emily Kress tells us more about how the eclipse can change how those waves work.
It's an all-day affair at the University of Scranton preparing for the total solar eclipse. While some students are just watching, others are working hard on research.
Yeah. A lot of velocity.
We're looking to see how this particular eclipse affects the ionosphere and the upper atmosphere. Every single eclipse is a little bit different, going through a different path.
Dr. Nathaniel Frissell is an associate professor of physics and engineering at the university. He says this research has been years in the making. Last fall, the university installed this tower to get a student ham radio station up and running at the Loyola Science Center. Students and other community members are able to connect with people across the country and the world.
When the eclipse comes through, it cuts off the sun and that photoionization, and so now the radio waves aren't bent the same way. And so when you receive the signals on the other end, or you don't receive the signals on the other end, if you look at things correctly, that can be attributed back to the eclipse.
Research like this is important because if we can understand how radio propagation works, we'd be better suited in cases like an emergency, where processes such as phone lines or any other electronic communication wouldn't really work.
Students spent all day in the ham radio station since other parts of the world experienced the eclipse long before the eclipse reaches our area. The university was one of 5 chosen as part of a citizen science project with NASA. Through this research, students are helping to document history.
It's a pretty cool experience. It's like the environment and how everything is, all the people around here. It's very interesting to see all play out.
That feels pretty great knowing that we're at the front of this, and would not have expected to have this great opportunity when I first came to the university.
Students will now spend their time breaking down all of the data collected. Emily Kress, Newswatch 16, Scranton.
So what does some of that data look like? Well, here's some of it. This is one of the first views we had of that data. It's a bit of an eye chart from the back of the room here, but we're breaking down. There's over 52.7 million ham radio data points plotted in this plot. And it's broken down into 6 frequencies. And the most important thing to note here is that in this part that says total solar eclipse, and I guess I can highlight it online right over here, this part that says total solar eclipse, you see more communications happen at the low frequencies at 1.8, 3.5, and 7 megahertz. And that's because when the eclipse comes over, that D region ionosphere starts to go away, and the absorption is removed, and that allows these signals to get through. You can also see very clearly in this plot the effects of nighttime. So this is night over here, where the high frequencies are not active and the low frequencies are, and day, where the high frequencies are active. They can cut through that absorption, but the low frequencies are not, except during the eclipse. So we also expect the eclipse to cause a depletion in the activity of these higher frequencies. And it's hard to see that in this plot. So we have a postdoc, Dr. Kuldeep Pandey, who works at NJIT on this project. He's been digging much further into this data. And so he's been making plots like this. So here you can see the 7 megahertz continental United States data. So here you can see that in more people are able to talk to each other on the ham radio due to the eclipse over the United States, and even further around the world. That's the global data on 7 megahertz. And here's 21 megahertz. This is one where you expect you to have less communications because the signals are escaping into the sky. It's interesting that it doesn't look like it caused much of a difference over the continental United States. But if you look at the global data, this depletion over here means that you have a hard time talking to the farther away stations, the ones that are, say, like 6,000, 8,000, 9,000 kilometers away. That was very much affected by the eclipse. And another interesting point that they noticed is that it's a little hard to see on the screen if you're sitting here, but the eclipse happened right over here on 15 megahertz. Or I'm sorry, on 21 megahertz, which is 15 meters. But the effect actually happened afterward, after the eclipse, and that was kind of a surprise. If you look at the control day, you don't see that negative effect. So that's something our Dr. Pandey is looking into more. But he thinks that has to do with the fact that the eclipse actually merged into the dusk sector right here. So having eclipse go right into dusk actually created some very unique effects. Now, in addition to just looking at the data, we can actually do this whole ray trace modeling as well, which I showed a little bit of before, where you take that ionospheric model and then you put it into the ray tracing program. And Dr. Pandey is also doing that ray tracing, and he's able to tell you things like, okay, it's these frequencies probably reflected off of the E region ionosphere, those frequencies reflected off of the F region ionosphere. So it's really interesting with these results. And here's a summary of these results, most of which I told you already. So that's the solar eclipse QSO party. The other experiment I wanted to tell you about is the Personal Space Weather Station GRAPE HF Doppler experiment. Now, the things you just saw really was like pure ham radio. Just ham radio operators talking to each other, and the reverse speaking network, WhisperNet, PSK reporter. Those are systems that were all designed by ham radio operators for ham radio operators, and we're just borrowing that data. With this experiment, we said, okay, we're going to create some of our own instrumentation, and we're going to deploy it. And we came up with these things called the Personal Space Weather Stations. Now, this last one over here, the Whisper Demon Grape, we actually just installed one of these over in the last hut over there this past Wednesday. So we now have one of these systems here at Jenny Jump. And one of the things we look at with that system is something called HF Doppler shift. So there's a transmitter run by the federal government called WWV in Colorado, and it's constantly transmitting on, say, 5, 10, 15 megahertz with a very precise frequency. And with something called the GPS disciplined receiver, you can measure that frequency very precisely at these remote stations. As the ionosphere moves up and down, that changes the frequencies that are observed. And so during the eclipse, we should be able to see this. Here's WWV. Here's the Canadian counterpart, CHU. Here's my house. And here's the results from the eclipse day. So right over here, we're listening to 10 megahertz. This is on October 14th, 2023. You can see that's fairly stable throughout the night. Then here's dawn. You get very large positive Doppler shift. So as the sun comes up, it builds up the ionosphere. The path lengths get shorter, and the frequencies that you receive increase. Then here's the eclipse. You get these negative frequencies, then positive, and then it goes constant again. You can see that on one. This is just on one frequency for the annular eclipse. By the time the total solar eclipse came, we had a system that could receive multiple frequencies simultaneously. So here are similar plots where you get all the different observations throughout the night, and then here's the eclipse signature right there. That's likely coming from Colorado. And then here's the same sort of thing coming from the CHU transmitter in Canada. So you can make these really neat plots. Let me talk to you a little bit more about what this Whisper Demon Personal Space Weather Station is. If you are a bit technical and you like working with Linux systems, you can actually put one of these systems together yourself. You just go to hamsci.org/whisperdemon and you can come up with these instructions. And note, this is still a bit experimental, so you're likely going to need some hand-holding as you do this. But one of the nice things about this particular system is that in addition to taking these science measurements like I just showed you, you can actually use it as a regular shortwave radio that you can listen to. So you can just go to a website and you can come up with a radio receiver like this, and you can actually listen to those same types of conversations just like I played for you earlier today. And with the system here, we do have a public-facing URL to this system, which I think they might eventually put up on the UACNJ website, so you'll actually be able to access this system that's here remotely from your house and listen to these. But that's the web interface for it. So what do these systems look like? Again, here's my house. We're using these little tiny B-Link computers, which cost about $300 each. So I actually have 3 different systems all set up right next to each other here. And we're using antennas that are fairly short. They're just a little bit taller than, say, a person. These are the ones at my house. Up behind the shed back there, in the woods, there's actually an antenna field that looks very similar to this. Now, in addition to being able to make those HF Doppler shift measurements, and in addition to being able to do these software-defined radio receiver that you can actually tune around and play with, you can also use it as a whisper receiver. So just like I showed you from the solar eclipse QSO party, how we were listening to those automatically decoding those stations from all around the world, this system will do that too. And so here's a screenshot that I took from the website of my system a couple months ago. But the system here is similarly reporting to whisper.rocks and whisper.live. So I want to, before we get into the question and answer, I just want to leave with one more thing. Did you know that you can communicate by bouncing radio signals off of the trails of meteors? Yes, it's true. So here at the Jenny Jump Observatory, I'm sure that most of you are familiar with meteor showers, right? When the meteors, when you have the meteor shower, those meteorites, they'll come through the upper atmosphere and they will burn up and you'll get a visible light. But in addition to that, they will actually ionize the gas behind them. It'll leave an ionized trail. And you have about a second where you can actually transmit a signal, have it reflect off of that ionized trail, and you can get it back to you. And we've known this for many years, and ham radio operators do this thing called meteor scatter. And what we want to do is, like we had the solar eclipse QSO party, we want to create a similar sort of ham radio experiment for meteor scatter. So I gave you those little cards that say meteor scatter QSO party, and so we now have a project where we're encouraging ham radio operators to get on during the Perseids and the Geminids meteor showers, which is August 11th and 12th and December 12th through 13th of this year, and try to talk to each other using meteor scatter and then send us your data. So let's see. So one of the really interesting things is that there was a recent law change which actually allows ham radio operators to use a meteor scatter mode on 28 megahertz that we weren't allowed to before, and that opens up a new research question because the theory says that the scattering process favors 28 megahertz or 10 meters, but there's another process called the initial trail radius effect that says the ionization trails of certain sizes can cause destructive interference to the signal. So basically, we're very curious to know, can you do meteor scatter better on 10 meters, which is 28 megahertz, or on 6 meters, which is 50 megahertz? And we're hoping that our meteor scatter QSO party will help answer those questions. So if you're interested in this, you can visit the HamSCI webpage, hamsci.org. For the meteor scatter, go to hamsci.org/msqp for more information. For HamSCI in general, go to hamsci.org. We have a Google group. We now have over 1,400 members. There's lots of information on how to get involved there. And you can also, like I said, I can help you find local clubs if you want to just get involved in ham radio at all. And certainly if you are interested in HamSCI, probably the best, if you're not a ham radio operator yet, the best thing to do is go get a ham radio license, learn about that, and then you can come and do some HamSCI. So thank you very much. It's been wonderful speaking to you this evening. I will be happy to take any questions.
All right. Thank you, Nathaniel. So we're going to get into the question and answer session. How that is going to work is for the people here, you're going to raise your hand and kind of wave it about and keep your hand up so I can get to you with the microphone so that everyone here can hear your question and the people online, because chances are if you have that question, someone else might too, but they might not be brave enough to actually ask it. Also, it generates follow-up questions, which are also very interesting. Online people, you just get to type because you have the easy job. Just a reminder, because I know people generally wander away, we are using our headlights when we go to leave. We are keeping our flashlights pointed towards the ground so we don't blind people unnecessarily. Porta potty in the back, it's illuminated by red if you need it. We also have a museum and gift shop in there, and we do have a couple telescopes that you will be able to at least look at, if not see anything, because it is still cloudy. All right, so I'm going to start with the question from this dude back here.
All right, so when it's nighttime, it's nighttime, it's technically nighttime right now, and the sun's not facing the earth at that time. How can humans survive without the sun,
How do humans survive without the sun facing us?
Yeah, at nighttime the sun's is not theirs.
Right. So
it's on the other side.
So the humans we depend, and all life on Earth depend on energy from the sun. But even when the sun isn't facing us, when the sun is facing us, it heats things up right away, but the Earth also stores some of that energy. So when we go around to the night side, the Earth doesn't get completely cold right away. The greenhouse gases trap some of the heat inside of the Earth. The ground itself holds some of that heat, and that keeps the heat and the energy enough through the night for us to survive.
That's kind of why around here we can live. On Mars or like the moon, there's such a drastic temperature shift between light side, dark side. But excellent question. Okay, so our first online question was, how did the kid who was 5-year-olds pass a federal exam with electrical engineering knowledge? Is it just a super easy exam?
No, it's not a super easy exam. It does require some studying. But actually, I'm friends with the person who was actually, he's not the youngest ham anymore, but he has the record for being the youngest ham in the United States. And so his name is Neil Rapp, and he's a wonderful guy. But yeah, his dad wanted to become a ham radio operator, and his dad brought little Neil along with him to the ham radio class. And at first they said, oh, people under 7 can't be in the ham radio class. But then, Neil showed some aptitude, and so they said, well, we'll let him stay. And then he proved that he could actually, at that time you had to learn Morse code. You don't have to do that anymore. But he was able to listen to all of the rules and regulations, and you learn basic Ohm's law, which is just, E equals I times R, voltage equals current.
Oh, just basic
which is, it sounds a lot right now, but again, if you do this over time and you work carefully with it and you're interested, you can do it. And interestingly, it's not a requirement to read to get your ham radio license. So like the test can be given orally. So if you do learn all the questions that way, even if you don't know how to read, the examiners can read you the question and then read you the answer, and then you pick the correct one.
All right, we have another question here.
So when about the where you could connect to the meteorite shower.
Mm-hmm.
How do you know exactly the second when to shoot out the radio signal?
That's a great question. You don't know exactly the second when to shoot out the radio signal. What you do know is that you know that there are probabilities. There are times where it's going to be much more likely that you're going to have a radio communication than other times. So if you do the communications during a meteor shower, it's going to be much more likely that the communications will work. So then during the meteor shower, you try to send out a bunch of communications, and some of them will go through and some of them won't. The ones when one does go through, you can then look at certain characteristics of the received signal, and then you can say, okay, based on how strong it was or really how much time the signal took lasted, you can say this is probably meteor scatter.
All right, we got another question over here.
I actually have 3 questions.
Okay.
1.
Okay, number 1. So is ham radio used for AM and FM?
So ham radio, AM and FM are what we call modes. So they're ways of encoding information onto a radio signal. So in ham radio, you can use either AM or you can use FM. Now this is not to be confused with the AM and FM. Like when you listen to AM and FM music or in your car, that's a different radio service. They're still using amplitude modulation and frequency modulation, but it's not ham radio. But the short answer is yes, ham radio operators can use both AM amplitude modulation and they can use FM frequency modulation.
Can I say number 2?
Yes, and then I'm going to go to someone else, and then we can come back to you, okay?
Okay. So number 2.
Okay.
When the sun becomes a black hole, will humans probably be intelligent enough to create their own ionosphere, whatever it's called?
Oh, that I have no idea. I don't even think the sun is on track to becoming a black hole.
So the sun actually isn't a large enough star
Right,
to
that's what I
become a
meant.
black hole.
But when the sun gets to the age that it's going to get to the next stage, we're probably not going to exist unless we have somehow figured out how to escape Earth and go somewhere else that's livable.
Yes, because as the sun's dying, it expands. So by the time it's a problem, it's already eaten Earth and Mars. So we're probably going to be off planet if we are still around at that point.
Yes.
Right. So our next online question is, should we be concerned with how much radio noise we are putting out into space? Does that interfere with some science instruments out there?
Oh, absolutely. And not just radio noise out into space, but radio noise here that we create here on Earth. So most of the radio signals that I look at are terrestrial signals. I focus mostly on signals here on Earth. And radio noise that we create is a huge, huge, huge problem. I live in a fairly rural area, and I have noise problems that I'm still trying to figure out, and I have got people helping me to figure out. And a lot of these cheap cell phone chargers, cheap switching power supplies, they have circuitry in them that will actually generate noise that even though they're not a radio, they'll still radiate this noise, and that can raise the noise floor of the whole planet.
Yeah, fun fact, your laptop puts out RF noise, not yours. We had some dude who built his own laptop. Major interference because these headsets also work on radio frequency.
Yes.
So, fun facts. I saw his first, and then I'll get to you, okay?
So can the ham radios connect to GMRS and FRS radios?
Not legally.
So
from
yes.
So
if you want jail,
you're probably not going to end up in jail for it. You could get fined. Most people, if you, I'll just say that the FRS and ham radios cannot legally talk to each other. And same thing with GMRS. You have to have GMRS type accepted radios to talk on GMRS, and you have to have a proper GMRS license to use that.
All right. I saw you first.
Is it true that the sun will stop shining in a few billion years?
I think so. Kim, do you know the current timeline for that?
Not right now. I have a feeling I've heard the answer a couple times.
Yes.
I think our observer Paul Fisher might know.
We will know, yeah.
Because he does talk on the life cycle of stars. So I have a feeling and I think he's around. So if you find one of our volunteers named Paul Fisher, he's the one you want to ask that question to. Because unfortunately that is not, again, one of the answers I have memorized. Right. So I'm walking to the next person. Our next online question is, you mentioned you have equipment in a shed at Jenny Jump. What specific science projects are you running and involved in?
I am specifically involved in the Personal Space Weather Station project, and that equipment is the one. That's this equipment here. We have a small computer, little software-defined radio called an RX888, and a GPS-disciplined oscillator. So I've got that equipment in the shed over here, and we also have a ground magnetometer. And there's other equipment in the sheds over there too, run by other people, such as Fabry-Pro interferometers and LiDAR systems.
All right, and our next question here.
In your time using the ham radio, have you ever heard anything where you say or decipher this isn't from Earth?
I have not. Well, you mean from intelligent life? So certainly things that you hear from
wow signals.
Yeah, so certainly things that you hear, like if you have a radio blackout where everything suddenly just goes away, that's not from Earth, it's from the sun. But I think you're asking, is there like some intelligent life signal? I haven't personally had that.
Right. So we got a. You could speak into the mic.
How old do you have to be to become one of these like scientist world things?
So to become a ham radio operator, you can become a ham radio operator now. If you want to do my job, like become a scientist like I'm a scientist, it's not so much how old you are, but you do need to get certain degrees. So
how quickly can you get through college?
Yeah, how quickly can you get through college? So I have a bachelor's degree from college, and then I have a master's degree and a PhD from graduate school.
Honestly, that sounds like a really fun goal.
It is. And what's really neat is and this should be true for pretty much anyone who's really interested in this, you know, graduate school is funded very often through research grants, like from the National Science Foundation, NASA. And so once you get through undergrad, you can, if you are working in a field like if you have a degree in physics or engineering, you can go apply to graduate school, and you could very likely get your entire graduate degree funded if you have good grades.
All right, our next online question was, why are you guys trying to make me take on more hobbies? And the answer to that I gave online was, because science is too darn fun for its own good.
I love it. I just found this so fascinating.
All right, so we had a number of questions back here.
Is it easy to tell what people are saying on the ham radio?
Is it easy to tell what?
What people are saying on ham radio.
It depends. Sometimes it's easy and sometimes it's hard. So if their signal is strong,
like talking into the mic.
Yeah, if their signal is strong and clear, then it's easy. If they don't have if they don't have a very thick foreign accent, then it's easy. But sometimes the signals are weak and they have a thick foreign accent, and it's difficult.
And do you think if a radio doesn't go back to Earth, do you think an alien might find it?
You never know.
Right. So online people, if you have any questions, do get those in. I like to say that, give them a little heads up now, because by the time they hear it, stream delay is a thing. We're already a couple minutes into the future. So our next question was over here.
Are ham radio signals traceable?
Sure. They are trace. If you persistently transmit, people can triangulate you. If you just transmit kind of quickly and then you get out of there and you don't do any more of it, it's going to be hard for people to trace you. But certainly with these networks of automated receivers, there's a lot of receivers out there.
Right, we got another question here.
Can ham radios connect to the Saturn radios that the Air Force uses?
The Saturn. So there's something called. Maybe I'll answer this a little bit more generally. Ham radios can listen to pretty much any frequency you want to listen to. There are very few frequencies that are blocked. They are, with a ham radio license, you are legally allowed to transmit on ham radio frequencies, which are not military frequencies. There is something called the Military Affiliate Amateur Radio Service, or MARS, where if you have a MARS license, you legally can use the ham radio to communicate with military radios in certain circumstances.
Right, our next online question was, you said they're personal weather stations, so can an ordinary person get or make one of the GRAPE stations?
Yes, an ordinary person can get or make one of the GRAPE stations. The GRAPE ones is something you can actually build, and the new one that I have on the screen right now, this Whisper Demon GRAPE one, yes, you can get the parts and you can build it, and you don't need a license for this. This is receive only, and you can do as much receiving in the United States as you want without having a license. It's only when you start transmitting that you have to have a ham radio license.
All right.
So I had a question about, so with space travel, can ham radio be used as a potential communication with someone, Mars, and the, Earth?
Yes, absolutely. In fact, all of the astronauts, the U.S. astronauts, they typically get their ham radio license because they use that as a backup communications in case their regular communications breaks down. So I think almost every single U.S. amateur radio license U.S. astronaut has a technician license or higher.
I know I saw a hand in the center here, but you put it down and you cease to exist. I don't have my distance glasses on, so it gets hard.
Sorry for the basic physics question. At the location where the radio waves originate, are they inherently unidirectional and then they have to be aimed somewhere to hit a place in the ionosphere to talk to Norway, let's say? Or are they omnidirectional and they require some kind of collimation to get it to go in a general direction, or maybe neither of those?
That's a great question. So it all depends on the type of antenna you have. So a dipole antenna is going to kind of emit donut shape, and so you might have it oriented east-west or north-south. And if you have a Yagi antenna, which is looks like a TV antenna, that will be more directional, and you'd actually want to steer it. So, and you also can have vertical antennas that are more or less omnidirectional. So if you have a less expensive ham radio station, you can start off with an omnidirectional antenna that pretty much just works everywhere. And if you get a more expensive ham radio station, you can get into fancy directional antennas that you can focus to get gain in a particular direction and help you to communicate in a certain direction.
So I'm going to say like 3 more questions, and then if you have questions, you can ask them after the presentation has ended. I know some people probably want to get out and go look at the telescopes. It still looks cloudy,
This is a follow-up question to some a question someone had earlier, but you said the ham radios are traceable if you use them often. If under the use of the wrong person, could they be seen as dangerous?
I don't think they're particularly dangerous. You know, they get dangerous if someone's willfully using them to say block or jam things like ambulance or police communications, then they might be dangerous. They're going to be dangerous if you are using high-powered amplifiers and you are not using them properly. They're dangerous. The other place where ham radios are dangerous are people will try to set up antennas and they will either fall off of towers or they'll have their antenna fall on top of a power line that'll cause a fire or kill them. But if you follow some very basic safety guidelines and you don't talk about anything illegal on the air, then they're not dangerous.
Right. I think I saw a question up front here. Are we just yawning? Even the cicada went away. I swear I saw some, and like I said, if you put your hand down, you cease to exist, unfortunately. Bueller? All right. So, thank you everyone for coming out. Once again, do check us out on our website, uacnj.org. Go check him out on the HamSCI website.
And I should say, when the academic school year starts up, so end of August, beginning of September, the University of Scranton ham radio station is open Thursday nights from 7 to 9 p.m. So we have public ham radio night. So you can come visit us, and I post the hours that we're open on our website, scranton.edu/W3USR, and that's on the little business cards I handed out to you, which we actually call eyeball QSL cards.
Because Scranton is a bit of a drive. Do you know of any other colleges or schools that might also do something similar closer?
That do public nights?
Yeah.
I'm not sure. You know, NJIT does have a club, but I don't think they have public nights the way we do. There are a number of ham radio clubs in the area. Sussex County has a really active ham radio club called the Sussex Amateur Radio Club. You just look them up, and they will you'll get information there. I was very active with the Ramsey Office of Emergency Management and the Bergen Amateur Radio Association when I was in New Jersey, so I know the MAWA people might want to look those people up. If you go to ARRL.org, that's the American Radio Relay League, they have a club finder there as well where you can get information on where to find local clubs.
No, don't go inside.
But come visit us in Scranton. It's only an hour away from here.
Don't let the frog inside.
I won't let the frog inside. And we also have the Steamtown Museum, so you can see lots of really neat steam trains.
All right. So like I said, thank you all for coming here and joining us tonight. Thank you everyone online for joining us. If you have any questions or you want to see some of the slides that maybe were a little hard because you're sitting in the back, you can find this presentation on our YouTube channel. And with that, everyone have a great night, clearer skies than the Saturdays we've been having, and good seeing.
Thank you, everyone. Or as we say in ham radio, 7-3, which means best wishes.